OK, so now we're going to change off of machine model and talk about other aspects of instruction set architectures. And to talk about what else is in instruction set architectures, well, there's the fundamental machine model, how many registers you have, what type of register access you have. Do you have stack-based? Do you have an accumulator? Do you have a register-register or a register memory architecture? Also, you need to talk about what the fundamental operations that you have, the fundamental instructions you have. So let's look at classes of instructions. You start off with things like data transfer instructions. So loads, stores, move to control registers. So this is what MIPS has. And in this course, we're going to be relying a lot on MIPS, the MIPS instruction set architecture, a lot for our example cases. But you have load, store, move to, and move from control registers with different control registers. You have arithmetic logic unit instructions, so things like adding, subtracting, anding, oring, multiplication, division. This is an interesting one here, set less than. That's kind of a fun one. It's a comparison operator. So if you want to take two values and compare and see which one's less than the other, you can use set less than. Load upper immediate. This is moving a value into a different location in a register. It's kind of like a shift operation. You can have control flow instructions. So you have branches, jumps, traps. And one of the points I want to get across here is within or between different instruction set architectures, people make different choices about which instructions to have. Some people have very complex ones, some people have very simple ones, or some of the architectures have very complex ones, and some of the architectures have very simple ones. You can have floating point instructions, adding floating point numbers, multiplying floating point numbers, subtracting floating point numbers. These are actually compare operations. Oh, excuse me, this is a compare operation, floating point numbers. So compare less than for doubles, or double precision floating point. Here we have conversion operations. So it's conversion from a single precision floating point number to an integer number, or integer word number. So this is a convert. This is the MIPS instructions. You can have multimedia instructions, or what's called single instruction multiple data. And we'll be talking about SIMD a bunch in this course later when we get to data parallelism and vector units. And this is actually an example out of x86 I wanted to give of stranger operations that sometimes show up as fundamental operations or fundamental instructions in instruction set architectures. This is an example called rep moves b. That's not two instructions, that's one instruction with a prefix and a space in between it. Yep. This is actually valid Intel assembly code. And what is rep moves b? Well, rep moves b is a string operation where it'll actually copy one string into another string. So if you have some text and you want to copy it to another piece of text, you can do reps move b and set up a number and it'll actually copy. This is the moral equivalent of something like stir ncopy. So you can do that all in one instruction. So in addition to these complex string operations, things like rep moves b, we can see there was sort of old jokes about adding extra and extra instructions and having really complex instructions. So for instance, in the VAX architecture, they had instructions that could do very complex things. I think there was one that even did a fast Fourier transform in one instruction. That's right, a whole fast Fourier transform or across a huge data set in one instruction. So you can see that there's a lot of different choice between your classes of instructions, and the ISA architect, or the instruction set architect, has to sit down and think about what should be in an instruction set versus being left out of an instruction set. Another characteristic of instruction set architectures that the architect needs to think about is how do you go and access memory? And what are the different addressing modes that can be used? So, or how do you get operands from memory? So looking at one example here, we have a register-based addressing mode. So in a register-based addressing mode, we can only name two registers and put them in another register. And this is a 3 operand format here. x86 would only have 2. But you can name register 3, register 2, add them together, and put them into register 4, for instance. And one of the interesting things here is this may not actually access any memory. We call it a memory mode, but it may not actually access memory. If you have enough register space and your implementation or your microarchitecture actually implements all the registers, then it won't go access memory. But it might access memory. So for instance, there are machines out there where you have a register, register, register operation or register, register, register instruction, but the processor has no register file. Everything is out in main memory. So it has to go read the data from main memory to go actually do the operation. And it just sort of caches or keeps the 2 operations that are needed. And it's all at the microarchitecture level. So this is all at the big A architecture level and asking what is the fundamental memory operations that can be done. So that's a register-based addressing mode. We can have immediate-based addressing modes. So here we have something like a constant of 5 being added to a register, put it into another register. So here's our assembly code for that. You can have displacement-based addressing. So in displacement, we're going to take a register value, add it to some constant, and then take that and look up in main memory that location, and then do some operation, let's say with another register. But this is displacement-based, and it's called displacement because you can take a register and have some displacement off of it. You can have register indirect, and this is pretty common on something like MIPS, or actually if you go look at the Itanium instruction set, they don't have displacement stuff. They only have register indirect. So this is similar to the displacement, but you can't have a displacement. You can only go and read from a particular memory address that's stored in a register. You can have absolute addressing. This is actually not very common on most modern day architectures, but in the older machines this was common. So you can take memory and take a constant, not out of a register, and go look up in memory and then do some operation with that. You can have memory indirect, and this is kind of interesting way to denote this here. MIPS very much does not have this, but you could do a memory operation of a memory operation of a register. So what you have is in a register, you'd have an address, and then you would take that address, you'd look up in main memory, get the data, and that itself is an address, and then you look up in main memory again with it. So it's sort of a double index based off a register sort of addressing mode. And that gets pretty fancy. So if you look at something like VAX, they definitely had this. You can have PC relative or program counter relative or instruction pointer relative addressing. So you can take the program counter, add some displacement, and then index memory. This is very useful for position independent code or code that you don't know where it's going to be loaded. And if you want to go access some data close to where the code is, you don't know exactly where the code is loaded, but the program counter, because you know what instruction you're executing, you can basically index off that and find memory around where you are, or around where you're loaded in main memory. So this is for PIC code. You can also have scaled. This is something that x86 has, where you can actually take a register and add it to another register multiplied by something else. So in x86, this is called SIB, scaled, index, and base mode. So you can actually take a displacement, add it to some 2 registers, and multiply it. And this is very useful if you're trying to index through an array of some size. So if you have an array of 4-byte words, you can just keep ticking up this counter here. So you start off 0, 1, 2, 3, and as this ticks up here, instead of going up by a byte, you'll go up by 4 bytes at a time. And if the data you're trying to load is 4 bytes long, you'll actually be able to just pick up the exact elements in the array you want, versus having to do this multiplication someplace else. Usually these scaled operations or scaled memory addressing modes have very limited sort of multiplication here. You can't multiply by, let's say, 7 Usually it's sort of multiplication by factors of 2 or a small set of factors of 2, because that's easy. That's just a shift operation in base 2. And then you can think about data types and their sizes. So what do I mean by data types? Well, you can have binary integer. You could think about having different types of integer data. You could think about having unary encoded, binary encoded. You can think about having things that are sort of roll in different ways. So for instance, as you probably learned about in your computer organization class, there's 1's complement versus 2's complement arithmetic. And that's different data types there. So you have binary integer data, and saying whether it's 1's complement versus 2's complement is pretty important. You can have binary coded decimal. So this is where each digit is encoded with 4 bits from each decimal digit, if you will, is encoded in sort of the point, or the period, if you will, is also encoded in there between your fraction and the integer portion, or the natural number portion. So your binary coded decimal can have different, very exact calculations for things like spreadsheets and business calculations. You can have floating point types, and there's actually a lot of different floating point types here. You can have, there's a standardization now that's called IEEE 754, which is what's used in most modern computers. And this was different than the Cray floating point on Cray supercomputers. They had a much wider floating point, and they also had different numbers of bits given to the mantissa versus the exponent. And by doing this, their precision could be different in different ways. So for instance, you could have a bigger range of numbers, but the precision smaller, or a smaller range of numbers with bigger precision, and there's different trade-offs there. Also, Intel internally, at least in x87, had this thing that they called Intel Extended Precision, which is 80 bits long. IEEE 754, the biggest thing defined in that is a 64-bit double. But if you want even more precision to your floating point numbers, you might need 80 bits. You can have packed vector data. This is like MMX data, where you're trying to pack the data all together and operate on it at the same time. So typically, things like MMX, you need to bring the data into a packed data type and then operate on that whole data type, so which has different values in it. And some architectures even have a special data type called addresses, which is different than a binary integer. So some older computers actually had address registers. And the address data type was different than the data type, or the binary integer data type. And that was different than the floating point data type. And there was different registers and different register names for that. And what was nice about that is they knew that if you loaded something into the address registers, it was definitely an address. So it had type information. And that's separate from the width. So let's say you have binary integer. Well, people have built machines which have 8 bits, 16 bits, 32 bits, 64 bits, all these different things as sort of the default word size. And then finally, one of the important things you need to do is come up with the encoding of the different instructions. And there's been a lot of debate on this of should you have fixed width versus variable width instructions. So let's look at a couple different ISAs and see where they fall, what camp they fall into. So most RISC architectures are fixed width. So you have MIPS, PowerPC, SPARC, ARM falling into this category. And as an example, MIPS, which we're going to be talking a lot about in this course, is every instruction is exactly 4 bytes long. And what's nice about this is it's easy to decode, but it may not be very compact. On the other side of this question about ISA encoding, you can see variable length instructions, where the width of the instruction can vary widely. So what's nice about this is you can have things that take up, things that are very common take up a very small amount of space. So if you have an instruction which is like 1 byte long and it's always called, you could effectively do a manual Huffman encoding on your instruction sets. So you take the most common things and you put them in the smallest amount of data. But if you have something that's very uncommon, you can have it take a lot of bytes. So an example here, x86, you can have between 1 and 17 bytes for an instruction. I think this has actually been updated now. If you look at x86 64, it can be between 1 and 18 bytes. So, and a couple ideas here. It can be everything in between, 1, 2, 3, 4, all the way up to 18. And some CISC architectures. You have IBM 360 is a good CISC example of a complex instruction set architecture. There's x86, Motorola, 68K, VAX. These are all variable length instruction encoding architectures. And now we start to get into something which is a little bit fuzzier. There's things that sort of start to cross over. People started to look at, started to build mostly fixed or compressed instruction set architectures. So example of this is something like MIPS16, which is effectively a MIPS instruction set where there is both 32-bit or 4-byte instructions and 16-bit or 2-byte instructions. And Thumb, which is the compressed or the mostly fixed instruction set architecture of ARM. Yep, gotta love the naming there. Also did the similar sort of thing where they had 2 bytes and 4 bytes as the different instructions. This is a little bit different than compressed. So this is like a mostly fixed architecture with sort of 2 different instruction sizes. If you look at something like PowerPC and VLI, some VLIWs, they actually have a compressed file, compressed format where they will actually store the instructions compressed and decompress them when it ends up in main memory, or ends up in the caches at least. So you can think of some architectures where the code in main memory is small, but then when you get to the cache, maybe it gets expanded or gets expanded when it comes out to the main processor. And then there's long instruction words where you actually can explicitly name multiple instructions happening at the same time, or even very long instruction words, or what's called VLIWs, which we'll be studying a bunch in this course, where you can put multiple fixed width instructions in multiple instructions in a fixed width bundle. So some good examples here are Multiflow, the LX architecture from, and also from STMicro. The LX architecture was from HP and STMicro, which shows up in printers today mostly. TI DSPs are actually VLIW architectures, and a couple other good examples. So just to show here something complex of how you end up with 1 to 18 bytes. Here we have x86's instruction set, and fundamentally you need an opcode, a byte worth of opcode. But some instructions might have between 1 and 3 bytes here. And then there's different addressing modes, special information about different addressing modes, displacements, immediates about the different addressing modes, and those all take up more space. And then you can also have prefixes. So that rep in rep moves B is actually a prefix which says repeat this operation multiple times. You can encode all these things in a variable with instruction format like x86. And to give you an example of something like MIPS, every instruction on MIPS is exactly 4 bytes long, and they have to fit everything into it. So a ISA architect or instruction set architecture architect has to decide the layouts of the bits within the instruction set, and that's usually something that's defined in the instruction set architecture. So to sum up some real-world instruction sets and where they fall with different numbers of operations, number of memory operations, data sizes, and registers, let's walk through a couple different instruction set architectures. And you've probably heard these in passing, but you may not have actually used any of these machines. But that's because some of them are embedded or some of them aren't commonly used anymore. But they're good to know about. So let's start off with Alpha. Alpha was built by Digital Equipment Corporation, and it's a register-register architecture with 3 named operands. There's no explicit memory operands in the instruction set. It's got 64 bits as the default data type. And when actually Alpha originally came out, you could only do 64-bit operations with it. That was sort of later changed as they figured out that might not have been the best idea. 64-bit addressing, and it was mostly designed for workstations, so big addresses, fast computers. Then you can see something like ARM. ARM is used in my cell phone. It's a architecture that there's a lot of different implementations of, and they've licensed it to lots of different people, but it's also register, 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 3 operands. There's a 32, and then now there's a 64-bit data size that has just come out. 16 registers, and the addressing, as I said, a 64-bit version came out, but is mostly 32. And it shows up in cell phones and embedded applications. MIPS, which is an outgrowth of the Stanford MIPS project, and later was commercialized. Register, register, register. We're going to be focusing on this mostly in this class. Sort of similar. Workstation embedded. Spark is another instruction set. This is what Sun originally used or used to use. It was an outgrowth of the RISC-1 and RISC-2 sort of architectures. It has, well, this one's interesting, between 24 and 32 registers, depending on how you look at it. They have this interesting idea where as you load more data in, or as you do function calls, data gets spilled out into main memory and gets pulled back in from main memory, kind of like a stack. So it's sort of a mixture between a stack and a register architecture, mostly used for workstations. You can see the TI C6000 is more for DSPs. But then we can start to see some more interesting stuff down here. Let's take a look at VAX. So VAX is a memory-memory architecture where it has 3 named operands, or could have up to 3 named operands, and all 3 of those can come from main memory. Has a relatively small number of registers. We can see something like the Motorola 6800. This is not to be confused with the Motorola 68000 or the 68K. This is the 6800. Is an accumulator-based register, or accumulator-based architecture, where you can have 1 named operand that comes from memory. It's an 8-bit data path, and this is mostly used in a microcontroller. So why all the diversity in these instruction set architectures? Well, instruction set architecture is actually influenced by technology, or influenced by transistor technology. So we see that if storage is limited, we might want tight encoding. And on the flip side is if you have very small number of transistors, you might want to try to fit the entire chip on there. And this was the actually fundamental idea behind RISC. If you have lots and lots of transistors, you might not have to worry about having to shove everything onto a very small amount of area. You can think about adding multi-core and many-core, start putting multiple processors on there and build an instruction set architecture specifically designed for multi-cores and many-cores. And then also instruction sets are many times influenced by their applications. So a good example of this is if you're building a signal processing architecture or a digital signal processor, a DSP, you might want to add DSP instructions. And then finally, I want to talk about how technology from software has influenced instruction set architecture over time. So if we look at something like the Spark architecture, it has what's called a register window. So in the register window, what happens is whenever you do a function call, it'll actually take 8 registers and put them into memory, and then you get 8 new registers. When you do a return, it takes 8 registers from memory and puts it back into your register file and sort of swaps out the ones that were there before. And what this was at the time that Spark was made, compilers didn't know how to do register allocation. It was like an open problem. Since that time, register allocation, figuring out how to take a fixed number of registers and move data in from a stack in main memory and vice versa, can be orchestrated very effectively and very efficiently by the compiler. But at the time, compilers were very simple, so people didn't know how to do that, so they needed hardware help to do that. So the instruction set architecture has that baked into it. But now that we have effective register allocation, we've not seen any other register windowed architectures come along after that. And if you talk to anyone who's actually went and implemented a Spark instruction set architecture, microarchitecture, They basically hate register windows. It's like the bane of this architecture. But at the time, compiler technology was not good enough. So applications influence it. Compiler technology influences your instruction set architecture. Technology influences your ISA. And ISAs have evolved over time, even though, as we said originally, a lot of times people want to build ISAs that don't change, so you can keep running software and have binary compatibility. But at some point, it might make sense to actually break that compatibility and re-optimize your instruction set architecture.